Hi. This talk is about making black box planning more efficient through the use of macro actions with focused effects. I'll be using the Rubik's Cube as an example problem throughout, but the method that I'll describe works for a wide variety of deterministic planning problems. We can visualize deterministic planning as a search tree, where our objective is to go from some arbitrary starting configuration, in this case a scrambled Rubik's Cube, to some desired goal configuration. Now, the cost of deterministic planning is exponential in the depth of this search tree. And one way that we will try to ease the computational burden is often to use heuristic search. And this essentially estimates the number of steps to the goal and allows us to do best first search, expanding nodes essentially based on the heuristic value. Now, I'd like to contrast black box planning with classical planning. In classical planning, we have an explicit action model, which, if we had a sort of a blocks world type of a problem, we might have an action that allows us to place block A on block B. And the explicit action model tells us the precondition and the effect of that action. So this explicit action model gives us some structure that we can use for solving the planning problem. Black box planning, on the other hand, does not have that structure. All we get is essentially the name of the action. And what we can do is we have a simulator that we can query in order to determine whether an action is applicable in a given state and whether, and what the effect of running the action is for a given state. So we don't have the explicit structure that we had in the classical planning example. Now, with classical planning, the heuristics can exploit the structure of this domain description in order to plan more efficiently and to get a better heuristic. Whereas in black box planning, we don't have any formal domain description to exploit. Essentially, we're limited to relying on goal counting for our heuristic. Now, the idea with goal counting is that we're going to count the number of state variables that still need to be fixed in order to satisfy the goal condition. So we can look at an example Rubik's Cube state here, and we can count the number of mistakes. So these are all the stickers that still need to be moved in order for the Rubik's Cube to be in the goal configuration. So we count those and we see that there are 6, and so we say that the heuristic value for this state is 6. Here's another state that we could count state variables for, and this is, in this case, we would get 20. And so for the cube on the left, we have a heuristic value of 6. For the cube on the right, we have a heuristic value of 20. And you might be thinking, wait a minute, the cube on the right, I can solve that in one step. I just need to do a counterclockwise turn by 90 degrees. And you'd be right. And so that's interesting. And if you know a lot about the Rubik's Cube, you might also recognize that the cube on the left can be solved in 14 steps. And so there's this discrepancy here between the heuristic, which is higher on the right, and the actual true cost of the planning problem, which is higher on the left. And so this tells us that the goal count heuristic is not especially accurate for the Rubik's Cube. And indeed, for many problems, it's not very accurate, not even just the Rubik's Cube. Planning is going to require a better heuristic in general. So if we just do greedy best first search with the goal count heuristic and the actions that are built into the domain, we see that we're never able to solve the Rubik's Cube in 2 million states, and that the number of errors remaining has essentially plateaued at around 9 or 15 by the time we reach the end of the planning budget. So this should give us some concern. And one question that we have to ask is, how can we make black box planning more efficient? The idea that we're going to explore in this talk is to discover macro actions that make the goal count heuristic more accurate. So we can visualize planning with macro actions using the same search tree as before. We're essentially going to add these macro actions onto the original actions. And each macro action is just a deterministic action sequence. So it takes some number of primitive actions and it combines them in a deterministic sequence, and now we have a macro action. These macro actions reduce the effective depth of the search tree because we can do multiple steps at once. That's good because it decreases the cost of planning, but the expense is that it increases the branching factor. So we have to do this sort of trade-off and make sure that we're adding useful macro actions. Now, one area where macro actions can be remarkably effective is in human expert speed solving competitions. So if you've ever seen one of these YouTube videos, the experts are able to solve the Rubik's Cube in a matter of single-digit seconds. They're very impressive. And the way that they do that is that they memorize sequences, these macro actions in advance that do particular things and help them in various scenarios. So if you get into a state that requires swapping 3 corners, hopefully you've already memorized a skill to swap 3 corners, and you can just simply execute the pre-learned macro action in order to get to the desired state. And it's unsurprising, but macros along these lines are actually very effective at planning, even just with greedy best first search using the goal count heuristic. So if we add the expert macros from the previous slide onto the base actions, we're able to now solve every puzzle only using less than 5% of the original search budget. So we sort of ask ourselves, why are the expert macros so effective? And what we're doing here is we're plotting the number of state variables modified versus the length of the action sequence. And so far, I've only plotted the base actions, which obviously only take one step. They also modify 20 of the stickers. And if you plot the expert macros on the same plot, you see that they modify many fewer state variables. Now, the hypothesis here is that maybe this is the fact that they're sort of more focused in some sense, that is leading to this planning efficiency gain. So we could also ask, what about other types of macro actions? What about random macros? So just arbitrary random sequences of primitive actions. If we plot those on the same plot, we see that they are nothing like the expert macros. They modify very many state variables. And indeed, this is what makes the Rubik's Cube such an interesting and challenging puzzle. We can also visualize the cost of planning with the random macros, and we find that they're not very effective. They actually make things worse. So whereas the expert macros made planning more efficient, the random macros seem to make planning less efficient. And so this sort of meshes with our hypothesis that the more focused the actions or the macro actions, maybe the better time we're going to have with planning with the goal count heuristic. And this kind of also matches with our intuition about what these macro actions were. So here's some of the expert macro actions that we saw from before. And what we see is that these are essentially only modifying specific state variables, and they're minimizing side effects to other state variables. So they have sort of this intuitive explanation of what's going on there. Now, the real question is, how can we automatically discover focused macro actions? Because we don't want to hand specify these expert macros for every planning problem. We'd like to ideally learn them automatically. And the way we're going to do that is we're going to start with an arbitrary initial planning state. In this case, we have a scrambled Rubik's Cube again. We ignore the goal information, and we just sort of consider some macro actions. So we look at our search tree, we consider a few candidate macro actions, and for each of these candidate macros, we're going to measure its effect size. The effect size is just the number of state variables that change from the start state of the macro to the end state of the macro. And we're going to ignore any changes that happen along the way. We're just looking at the final state and the initial state, and we're saying how many state variables have changed between state 0 and say S1. And so we can measure this effect size for a couple of these candidate macros. Maybe we get 14 state variables, maybe we get 8 variables for the next macro action, and so on. And so we'll say that the macros that modify the fewest state variables are the most focused. This allows us to essentially do best first search, expanding nodes with the lowest effect size first. Now, before we were using best first search for the planning, here we're going to use best first search for the macro learning. And whereas before we were using the goal count heuristic, now we're going to use this lowest effect size heuristic. And what we'll do is we'll store the n best macros in a library. And then when it comes time to do planning, we will augment the base actions with the learned focused macro actions. Now, before we do that, let's just visualize what the focused macros look like on this action plot. So if we plot the focused macro actions, we see that they're actually quite similar to the expert macro actions. They modify very few state variables. And if we visualize what these macros look like, we find that they have intuitive explanations as well. So similar to how the expert macros changed a few state variables, here's a learned 3-pair swap macro that our macro learning process discovered. And it also has sort of an intuitive explanation. This is almost the kind of skill that you could imagine a human using in the speed solving competitions. But what's more encouraging is not just that the focused macros look kind of like the expert macros, it's that they're beneficial for planning as well. So if we return to our greedy best first search planner with the goal count heuristic, and we add the focus macros onto the base actions, we find that they're able to solve the cube quickly and reliably in under 1 million states. And this is really encouraging. One thing that is even nicer is that the macro learning process is goal agnostic and is instance agnostic. So we only need to learn the macros for the first planning instance, and we can actually reuse them for the rest of the planning instances. That's nice because it means that the time that it takes us to learn the focused macros can be amortized over the number of planning instances. So in this case, we have 100 planning instances. We can actually divide the cost of learning the macros by 100. Now, even if we don't do that, the budget for learning the focused macros was only 1,000,000 steps. So in the case of the Rubik's Cube, if we offset the planning time by this budget for learning the focused macros, then we still are able to solve the Rubik's Cube 100% of the time within the 2,000,000 state planning budget. And that's really amazing because it means that we were able to both learn the focused macros and plan with them and solve 100% of the problems, whereas with the base actions alone, we couldn't solve any of the problems in that same planning budget. To summarize, focused macro actions, they make the goal count heuristic more accurate, they improve the efficiency of black box planning, and they can be discovered automatically. So a few things that I didn't have time to talk about today. First, that the focused macros are useful for a wide variety of planning problems. We've focused on the Rubik's Cube here, but we also looked in the paper at a number of other classical planning problems that we were able to convert to black box planning problems. And another thing is that the focused macros can generalize to novel goal states. So I said when we were learning the macros that we can throw out the goal information for the sake of learning the macros. This allows us to change the goal, and the same macros can still be applied in the situation. And finally, these macro actions that we're learning are also compatible with more advanced heuristics. So I focused on the goal count heuristic in this talk, but we tried looking at more advanced and sophisticated heuristics that incorporate things like state novelty into the mix. And we found that the improvement with the focused macros was there as well. I didn't have time to talk about these things today, but please check out the full paper if you're interested, and thank you for listening.